Hi, this is Lisa Knight. This is the first of 3 lectures on Newton's laws. In this video, we're going to concentrate on force and mass, distinguishing between them. Then we'll start talking about Newton's laws of motion, beginning with Newton's first law and his second law. In the second of the videos, we'll be finishing our discussion of Newton's second law in the vector nature of forces. In the third video, we'll be talking about weight and normal forces in the third law. So force and mass is a very basic concept in physics, making sure that you know the difference between a force and the difference between mass. Force, by definition, is a push or a pull, and it is a vector. It has magnitude and direction. Forces, in this case, the force or the tension in the rope is being applied by this young man as he pulls the sled across the ground. But notice that the rope is held up at an angle, so the tension, the F, in the rope is a force directed along the rope at whatever angle the rope makes with the ground. So the magnitude of the force would be the length or the numerical value of the tension, and the direction would be the angle relative to the ground. This means that as he pulls it upward at an angle, that he's lifting up on it, and at the very same time he's pulling it horizontally. It's important to note that the tension isn't what's moving this sled. It's the horizontal component of the tension, Fx, that's moving the sled. The last thing to remember is that force is measured in newtons. It's a kilogram times a meter per second squared. Mass is measured in kilograms. It's really a measure of how hard it is to change an object's velocity. The more mass something has, the harder it is to stop it, or the harder it is to keep it going. Mass can also be thought of as a measure of the quantity of matter in an object. It never changes from place to place. So a person that weighs about 115 pounds has a mass of 70 kilograms on Earth, on the moon, in the middle of empty space. But the weight of 150 pounds is only the weight on Earth. It changes from place to place, and we'll talk about that later. Newton's first law of motion. If you stop pushing an object, does it stop moving? Not necessarily, right? Sometimes it'll keep going, and sometimes it'll come to a stop. So imagine just giving a pen a little push and then watching it roll across the table. If the table and the pen are super smooth, it'll keep going forever and ever and ever at whatever speed you gave it. But if there's friction, eventually it'll come to a stop. But in the absence of any external force, the object will keep moving at that speed that it left your hand in a straight line. Or, if it was at rest, it'll stay at rest. This idea is known as the law of inertia. The law of inertia is attributed and is called Newton's first law of motion, but is not in fact Newton's original idea. He is the first to realize that it didn't just apply to things on Earth, it applied to the moon and to all things in the universe. The first person to really describe motion in human history was Aristotle. But unfortunately, he based all of his ideas on observations, and sometimes he came up with things that didn't make sense. His view of the world was that solid objects always wanted to come to a rest, and he used that to explain why when you held something up off the floor and you let go of it, it always fell. Or if you tossed it up, it would always end up falling to the ground because it wanted to be at a state at rest. What he didn't realize was that there was a force, a gravitational force of attraction between the object and Earth that was pulling down on the object and making it speed up towards the Earth. If there had been no gravity, it would have just hung there in space. Or if you tossed it straight up, it would just keep moving at whatever speed it left your hand moving at. It wasn't until Galileo came onto the scene that he was the first one to see that objects traveled at a constant speed or stayed at rest. And so he kind of changed the description of the natural motion of objects. He said either an object will stay traveling at a constant speed or it can stay at rest. Because they wanted to resist a change in motion. This resistance to a change in motion he coined as the inertia of the object. Turns out to be proportional to the mass. The more mass something has, the harder it is to get it moving, and the harder it is to stop it moving. Newton was the first to apply the law to all objects in the universe. So the first law of motion says an object will stay in its same state of motion, rest or constant velocity, unless an outside force acts on it. And this is true in inertial frame references. What is an inertial frame reference? It's a frame of reference or a situation that's not undergoing acceleration. So, for example, the Earth is rotating. It rotates at a constant speed on its axis, and it's rotating around the sun at a constant speed. This law holds true on Earth, so that is an inertial frame. So the Earth is not accelerating it and getting faster or slower as it spins on its axis. So since the law of inertia works for the Earth, it's considered an inertial frame. And it works because, and it is an inertial frame because it itself is not accelerating. So now let's talk about force, because force is what changes the inertia of something. In order to change its state of motion, right, to cause a change in its state of motion, you have to apply a force to it. So what is a force? Well, a force can be measured using a spring balance. And these spring balances are showing you that, if you hang a mass on one spring balance, it'll stretch the spring a certain distance. And if you hang twice the mass, it'll stretch it twice the distance. So you can kind of estimate how much force is being pulled with that spring gauge. So let's now apply the force to a mass. What we know is that if we apply a force to a mass, it'll make it accelerate. And the force is proportional to the acceleration. So if I double the force, the acceleration will double. But also we know that if we mess around with the mass, we can change the acceleration. So imagine that we apply the same force to twice the mass. It will have half the acceleration. Acceleration is inversely proportional to mass. So Newton's second law combines these two observations and defines what acceleration is. Acceleration is the ratio of force to mass. It's how much force divided by mass there is acting on an object. And we usually rearrange it, and you are used to seeing it as F equals ma, where he defines how to calculate a force. A force produces an acceleration in a mass. It's equal to the mass times the acceleration. And that's why we measure it in newtons, kilograms times meters per second squared. So you'll see Newton's second law stated as the net force is equal to the mass times the acceleration. We're going to use mass in kilograms and acceleration in meters per second squared so that we can calculate newtons. But be aware that there are other units of force. A dyne is a gram times a centimeter per second squared, and a pound is a slug times a foot per second squared. So when we start looking at forces acting on objects, it's important for us to sketch all the forces that are causing or interfering with the motion of that object. And this is called a free body diagram. And what we do is we actually take that object of interest and we isolate it, and we decide which way is positive or negative. That's called choosing a convenient coordinate system. And we draw in the forces, and we make sure that we resolve the forces into its components. And we apply Newton's second law to each coordinate direction. So, for example, a person's holding up a book, and if you were to draw a free body diagram of that, we would imagine that all the forces are acting on the center of mass of that book, so we draw a point in the middle of the book. And one force would be the weight, W, pulling down on it. And since it's not accelerating upward or downward, we know that the hand is pushing up equal and opposite to it. And so we're going to draw an arrow representing F going up. That's the same length as the weight going down. So the net force on the book is 0 because it's not accelerating upwards or downwards. The two vectors are the same length pointing in the opposite direction. Here's an example. A 1,000 kilogram box is accelerated with 200 newtons. If the mass of the box is cut in half, what will be the new acceleration of the box? Well, first let's find the acceleration of the box to begin with. So I drew a free body diagram. I drew my box sitting on the table, and the force that's acting on it, moving it, I've drawn here with an arrow. That's F. And F is causing the mass to accelerate. F equals ma. So number 1, I draw a diagram. Number 2, I write F equals ma. Number 3, I fill in the missing information. 200 newtons is making the 1,000 kilogram mass accelerate. So the acceleration is 2 meters per second squared. So what would be the new acceleration if I cut the mass in half? Well, it's an inverse relationship, right? If I decrease the mass by half, then I increase the acceleration, so that's twice as much. It'll be 4 meters per second squared. So if a 1,000 kilogram box is accelerated at 2 meters per second squared by a force, how much force would be required to accelerate the 500 kilogram box at the same rate? So now we're looking at this a little differently. Instead of looking at the effect the mass has on the acceleration, we know what the acceleration is, and we want to see how much force would be required to get the same acceleration from the half the mass. So once again, F equals ma, but this time we're going to plug in 500 kilograms for the mass and 2 meters per second squared for the acceleration. The force required would be 1,000 newtons. So let's take this a step further. Sometimes we don't always know what the acceleration is directly when we have to calculate it with the kinematics equation. So if I take an example here, a 1,000 kilogram car goes from rest to 30 meters per second in 5 seconds. Find the net force acting on it. First, let's list what we know. VI is 0 because we start from rest. VF is 30 meters per second. Time is 5 seconds. So in order to find the force, F equals ma, we have to have A. So we're going to look for A in this problem. The formula we'll use is VF equals VI plus AT. When I plug in my numbers, I'll get an acceleration of 6 meters per second squared. Now I can answer the question. F equals ma. 1,000 kilograms times 6 meters per second squared is 6,000 newtons.